Another draft physics presentation brought to you by. Anyway, so moving charges producing EMF kind of a thing. Why that happens. Why this idea that you have to move an electron to create energy or an event, however you want to describe it. So I've used this as an analogy. Space shuttles being launched, or rockets. You could say any old rocket will do. And so you have a rocket. And the rocket has big giant... put it in the middle of the thing here. Yeah. Big giant flame coming out of it. Okay. And the thing to think about is the fact that, so this is your, Newtonian sense. This is energy going one way. And you have your opposite but equal reaction, which is you have just as much something happening going this way. And obviously you don't see it as a big giant flame when the shuttle works properly. You just see the shuttle vibrate a little bit and shake, and it moves. And so all of this is essentially inside of the shuttle. So inside the shuttle, it's capturing this. So every second that this is doing this, there's a second worth of that kind of energy going inside the shuttle, and it stays in there. Because the shuttle goes 5 miles an hour, and it goes 10 miles an hour, and it goes 15 miles an hour, and it goes 20 miles an hour. It keeps increasing its speed every second as this flame that shoots out and turns into mist and clouds and stuff, that same energy goes inside of the shuttle and stays inside of there. I mean, we don't see it, but you would see it if you crashed the shuttle going 20 miles an hour into a wall. You'd see it in the sense you'd see just as much like little bits of stuff flying off and all kinds of action and stuff and explosion, and you'd see this say it was 10 seconds of this flame energy. 10 seconds of this flame energy you get all back if you crash this shuttle into something, because the faster it goes, the more spectacular the crash is going to be. The more damage it'll do to the thing it hits, and the more it will turn into particles. So the idea is that velocity is a real thing. Velocity is something made of something, a flame, that is now captured inside of something as potential. And so it's in there. Just as much pressure is now inside of this shuttle when it's got velocity. Alright. I think that's a pretty good explanation. You could do that in 6th grade with kids, and that would be a good way to explain it. Alright, anyway. So now you have an electron. So electrons are kind of like shuttles, except unlike a shuttle, they're not made of atoms and structure. So there's no mechanism inside of an electron where it can store flame. So when you push it, you can't make it go 10 miles, then 15 miles, then 25, then 30, then 50. You can't go higher and higher with the same flame. So when you have the same flame on it, burning, pressure, a voltage, pushing it, for some reason, okay, that pressure doesn't stay inside the electron. It loses it, because it can only be accelerated 1 second at a time, one flame worth, and then somehow that flame worth in that 1 second, it leaks all out, and then you have to have more flame for this second, and then this second can move it. So in gravity, for example, at 10 meters per second, an electron will just fall 10 meters per second. It won't go, it won't start gaining velocity. So it won't increase its speed. It'll just go, if 10 meters per second is, let's say, 20 miles an hour, it'll just go 20 miles an hour forever. If you could make the gravity forever, it can't go 40 miles, 60 miles. So when you jump out of an airplane, you start going faster and faster and faster, because you're adding velocity through the acceleration. So every time gravity accelerates you, the acceleration stays inside of you. So you just keep adding and adding and adding acceleration. But electrons don't do that. So first I'll explain the reason why they don't do that, and then I'll explain that what you're really seeing with EMF is the flame coming out of the perpendicular of the electron. So if you thought of it that way, the energy that's pushing it, the voltage that pushes the electron, essentially leaks out the sides. The electron still goes, because at every second it's being pushed by new energy. But so as long as there's a constant supply of little beads, let's say, little cannonballs you're hitting it with, as long as you keep shooting the gun, shooting bullets at it, it'll keep going. But each bullet does pop out the sides. So it doesn't collect the bullets. It only has one bullet worth all the time that it holds, but it doesn't hold any more than that. That kind of thing. Alright, so the reason it's like that. Okay, as I explained, trapping velocity, doing the space shuttle thing requires you to have atom bits, mostly probably helium nuclei, which all the complex atoms essentially have multiples of helium nuclei. And those are the only things that can trap this force as something where they can trap more and more and more of it and accelerate faster and faster, move faster and faster and faster, and turn an acceleration into a collective velocity. But these little elemental bits, the proton and electron, can't do that. So you can't shoot. I can't sit out and out here. Here's the Earth. I can't go out into space here, and I can't just shoot an electron and make it hit the moon. Just won't happen. It's run out of gas. So I could shoot it really fast, but it won't matter. It'll just run out of juice. Alright, so this part gets a little bit more complicated in a sense, because you sort of have to understand, if I was to describe an electron, I guess we just use this as an electron now. It was the Earth, but we'll make it an electron now. And understand that what it is a collection of a tendency and a direction. So it has a geometry or a little gyroscope in, however you want to look at it. And in all three of the dimensions and all six of the facets of the dimensions. So you kind of understand that if this is looking down at a circle overview, the dimensions are facets. This is one dimension, the two sides of one dimension. And this is the two sides of one dimension, and then this up into the paper and out of the paper are the two facets to one dimension. So there's kind of a 6 dimensions, really, in a sense, 6 subdimensions that make up the 3 dimensions. But anyway, so the electron has, say, energy in those configurations, in those 6 directions, and so in and out, forward, back, left, right. You could just think of them those simple way. 6 things. And when you hit it with something, you create a bias in that direction, in the sense that it absorbs that direction and it releases something in some other direction. So it'll give up going left or right, and it will collect going forward, let's say. And so it's a little calculator of momentum. This might be the reason why also electrons don't fly very straight as a tendency, is because they do give up maybe left and right, but that part isn't really important. The important part to understand is that the balance can end up biased. So you could sort of understand that it could have equal amounts of stuff going left and right, but it could have more stuff going forward than it has going backwards. And in that sense, it will move in that bias, in the direction of that bias. It'll go that way because there's 2 things pushing it that way and only 1 thing pushing it that way inside the mechanism of this electron. These could be the quarks. Just kind of depends on how how you want to visualize it. It's just the mechanical system of the electron has the capacity to do these exchanges, to essentially exchange energy. Now what it's really exchanging is two different polarizations. That is energy that's moving in one plane that's of one type, and this other type that we could say was black. And these two are being interpreted in the sense that they're allowed to interact with each other inside of electrons. So if a black energy hits the electron, it's a pure reflection. The electron reflects it back and gains the momentum, the extra bit, this way. So essentially it's exchanging this, which it releases here. So this direction leaves is the reflection, and it keeps this direction here. So it ends up with more stuff going this way and less stuff going this way. So you can understand is that's kind of a simple thing. And one of these other things hits it, the proton force. So that's what happens when an electron force hits it. When proton force hits it, it ends up doing the perpendicular thing, wherein the exchange will be it will essentially redirect this red energy and have it pop out perpendicular. But I don't think you need that for this electron explanation. I don't think you need that much detail. So let's move to the important part. So when when charges are, when they say something like a charge is moving, so that's any time you're creating these little force bits. And so the thing to understand is, like with magnetism or whatever, that these force bits are being segregated. So the magnetism essentially is creating a circumstance where there's all brown bits doing one thing, black bits, and all red bits are doing something else. So they essentially, a magnet segregates the force. And what that does is it segregates the impact on the atomic structure. So if there were electrons and protons, so we'll make the proton red. If you're getting hit, if this electron-proton arrangement is getting hit by the black energy, the electron energy, so we'll mark it electron, proton, you could sort of understand that the energy as it hits it, the brown energy, is going to push the electron this way, and it's going to do the opposite to the proton, which will end up moving this way. So you're pushing one and you're pulling, essentially, not essentially, superficially. Yes, it looks like a pull, it's actually a push, but anyway, it's attracting the proton, repelling the electron, and vice versa with the opposite force. And so when you're doing that, you're pressurizing the electrons, so you're creating more energy between constituent electrons. So obviously when you push an electron, the odds are, inevitably, like all the time, whenever you move an electron, you're actually pushing it against other electrons somewhere. Somewhere there's another electron, and those two electrons now have a higher pressure between them. Whatever force is between them is now bouncing at a higher frequency because of the closer proximity. So it's creating more pressure inside that system, which causes that pressure, as in essence, means that any movement of this electron will move this electron, will move this electron, will move this electron. So that's the chain reaction that you perceive to be electrical potential or movement or voltage or whatever. Now the actual voltage is in this pressure here, but the point is the electrons feel the pressure and move. Now the trick when electrons are moving in a conductor, so when you start to move them, accelerate them, that's all you can do is accelerate them. And so the individual electron circumstance is what we'll focus on. So each individual electron is being accelerated, being pressurized, and I'll just try to attempt to draw just that one individual circumstance. So what happens in space because the energy is coming from the outside, from everything. So everything's constantly bombarded by all this energy. And so if I was to accelerate an electron, move that up a little. So just think of these arrows going all the way around, and they're both polarizations, red and brown, blah, blah, blah. So if I was to accelerate an electron, that is, give it an imbalance, so it has more arrows going this way than this way. So the electron's moving this way because it's being pushed by more pressure coming from here, a voltage. Okay, so they apply a voltage, the voltage pushes the electron accelerates, it means it starts to move. But what's happening is external pressure, that is the constant pressure coming from the field, alright, is essentially going to do the same exchange game, and it's going to end up hitting this force will interact with this imbalance in a consistent manner. It does this all the time. And so when they're even, it's going to change these two sides equally. So if there's one, if it has the same force going both directions, you can sort of understand that exchanges from these sides would always end up being the same. You know, it would take one arrow going this way one time, the next time it would take an arrow going this way, the next time this way. It would be heads and tail flipping. They always come out the same in the end. But if it has a higher proportion of energy going one way, then it's more likely to make that exchange with the energy going in the direction of more. So if there's two here and only one here, that essentially means you get more tails than you get heads. So you'll affect the energy in this direction more often by just the laws of probability because there's more of it. So there'll be constant exchanges happening in the environment. These exchanges, in the sense that this black energy will go in, it will effectively convert this reflection. It will reflect this way, and it will in that exchange the end product will be that an arrow going this way will be exchanged for an arrow going this way, and so this imbalance will be taken away. Now at the same time, the arrows are doing it this way. I'm just saying that any imbalance will be hated essentially by this field, and as long as the field has balance, then the electron will duplicate that balance, so it can't stay imbalanced. That's sort of what I'm getting to. I mean, if it's to be more accurate, it's probably the proton arrows, okay, that are doing this exchanging with the the perpendicular direction. But both of these arrows, I guess I should have drawn them from the beginning in the diagram just to be explicit and correct. Because they're doing the perpendicular exchanges. So the point is that your odds of having an impact with this energy, it's more likely you're going to hit the side that has two of them than it is the side that has one, just because there's three things, two of them are going one way, one of them's going the other way. The odds are you're going to hit one of the ones going that way. And the exchange will essentially be, as I stated, it'll just neutralize one of those and it will release energy in a direction. So essentially the black energy, the energy that was pushing the voltage, that was pushing the electron, is essentially given up very quickly, and it'll be given up as energy going perpendicular to the movement of the electron. So the electron will give up the forward energy as perpendicular energy. I guess I should write it as a red arrow, because that's what it'll be given up as, as the opposite polarization. Opposite, is that correct or not? Correct enough for right now. So the fundamental point is that electrons can't maintain their velocity because there's always force interacting with it constantly. The force, if it's balanced, is going to is just by the laws of magnitude. The force is really big, the imbalance is very small inside the electron, and it's basically just going to absorb that imbalance and throw it back into the field. So the electron is essentially, as going back to the original drawing of the space shuttle thingy, the electron is essentially just going to outgas or give up its velocity in the form of energy leaving perpendicularly. And the perpendicular thing is just a rule. That's just the way the mechanics work. The idea, as I've drawn it before, is that that's fundamentally, you can have different kinds of collisions. You could have head-ons. Now, a head-on collision by two things is sort of an invisible collision in kinetics, because if they hit, the world will look a certain way, and if they miss, the world will look a certain way. And the idea is the world's always going to look the same way. If they hit or miss, there's be one thing going this way and one thing going this way. So if this is a reflection, or if this thing is going straight through, or these things miss, it doesn't matter. The universe always will look the same way with that kind of interaction. And the same is true of perpendicular interactions, but they get more, interesting in the sense that you can see the difference. So there will be a viewable difference if you have polarization. If you have some unique feature of the force, you'll be able to see the effect of the force. So you can't just say it's the same universe if they hit or they miss. It obviously isn't, because you're changing the direction of a particular polarization of the force. Let's see, do we need anything else? So the idea is when the electron's moving in a direction, but because it's got a voltage, the higher pressure on one side than the pressure on the other side. And so the pressure pushes it in closer proximity to other electrons. The other electrons also are tended to be pushed in that direction. And so everything just tends to get to increase the pressure, which is the distance between the electrons. So you're making them closer together. So the more voltage you apply, the closer together all the electrons end up tending to be. And if you get them close enough, you'll just have the electrons will start jumping each other's positions. But regardless, it's just the pressure that you're really moving, and the pressure moves at the speed of light. That's why the voltage moves the speed of light through the circuit. The electrons don't move that fast. The voltage moves that fast. The electrons don't really move. They're just vibrating, actually, but I don't want to get into that argument. But the idea is as you accelerate them, that is, as you're moving them closer together, so there's little tiny movements, but they're real movements. They're real accelerations in a direction. So they're all accelerating a little bit, and when they do that, acceleration is essentially, for an electron, acceleration is the same as deceleration, because they decelerate right after they accelerate. So they move, and then they they give up that energy right after they move. So they move, and then the field kind of just converts that energy, and so they're basically admitting new force to the environment from their perpendiculars, which, say, in a conductor, so when the conductor is doing that, this is going to be received by the outside world as magnetism. So that's the magnetism that the electrons are creating. And then that energy ends up, if it hits some other electron, it ends up creating new acceleration in another electron. And then that electron perpendicularly creates more force, which, if it's in a conductor, will be voltage. So the magnetism comes in, creates voltage. Okay, so the force. So when you move an electron in, because you're hitting force on it, pushing it this way. All right, so you're pushing the electron this way, it ends up releasing the acceleration, that is the movement you're causing. It ends up leaving the force leaving perpendicular, which will be in line with the other electrons, which means you're creating voltage in the other electrons. And then you move the other electrons that are moving this way, and then they'll create force coming out, which will end up be what will be considered magnetism. So they're constantly exchanging voltage and magnetism. They're constantly converting one into the other. Every time they move, they're either going to cause a higher voltage in a neighboring electron, or they're going to create magnetism, which is because there's not another electron. So magnetism and voltage are exactly the same thing, essentially. And they're the electron force. The protons are doing the same thing. It's just we don't get to see it because protons move much less, and they're in the nucleus, and they don't create any effects that are obvious when it comes to their role in the voltage isn't as obvious, but they're also being affected just as much as the electrons. Is the way to say it correctly. But it's just not as visible because the electrons are on the outside of the system and the protons are on the inside. So we see what happens on the outside, but we don't see what happens on the inside. But the same thing is happening. Protons are also emitting force, and they have the same acceleration rules. So when you move the protons, they're doing the same thing in terms of creating the force that to them is also voltage, and is to them is also magnetism. Well, close enough. So I don't think I'll try to go any further at this point, but it just explains this intimate relationship between electrons, magnetism, and electricity, and how it's just because electrons can't hold velocity, they have to release any force that affects them. They'll release force. Like I said, they obviously consume while they're moving the force, but only while they're moving. They don't hold any force, so they can't maintain any potential. They can't, well, as I stated, they can't acquire a true velocity. So velocity is when you're storing energy. So electrons can't store energy like atoms can. So there's no so anything that goes in is coming out quickly. It's not gonna go in, stay for a long time, and then go out. It's going to go in and come out quickly, delayed, but soon. And that delay has something to do with inductance and how fast you can move, how fast you can have systems communicate with each other. The point is it has to go through this acceleration process, which takes time. Electrons don't accelerate at the speed of light. They accelerate much slower, and they decelerate slower. And that's what creates all the time delays that creates the idea of inductance and the idea that you can't vibrate circuits at certain speeds and they won't work anymore, is because you can't make something go faster than the electron's ability to absorb the acceleration and then to decelerate. It all does take some time. Alright. Yeah, that's probably enough for a first installment on this specific subject and such. Yeah, I think I'll leave it there. Till next time and such.